There we go. Okay. All right. Well, we wasted about 15 minutes.
Well, John Bally here from the University of Colorado Boulder. John has spent most of his career there, but first he spent about 10 or 11 years at Bell Labs, like some of the greatest radio astronomers in America. They were all there. I suspect that John doesn't necessarily consider him just a radio astronomer, because if you look at his work, one of his strengths has been to be able to combine everything from the electromagnetic spectrum into one global picture of star formation. That's really his strength, in my opinion. But anyway, his main interest has been star formation, interstellar medium, and more recently, planet formation. And with one particular topic at the heart of this, which is like the interaction between stars and the interstellar environment, like the feedback from stars, to try to understand the dynamics of the interstellar medium. And I think you probably invented the molecular outflows with the Bally and Lada 80-something.
83.
83, yeah, there you go. And so he's really one of the fathers of stellar feedbacks and the study of stellar feedback. And in fact, that's also today's topic. And I think we may get a hint about his ability to explore the whole electromagnetic spectrum to understand star formation. Okay.
So I was in a group that discovered the cosmic microwave background, but many years after. That was at Crawford Hill. Spoiled rotten, by the way. So this is an example of multispectral view of Orion. This is the core of the Orion Nebula. You can see the Cartesian stars that light up the nebula. And in the background is an ALMA image of the explosion that happened 550 years ago in Orion. This event, by the way, is about 10 to the 48 ergs that release more energy than the sun puts out in about 10 million years. And this happened only 550 years ago, plus 1,300 year light travel time, of course. Too bad some monk in Ireland didn't have an infrared telescope around 1400. They would have seen a spectacular infrared flare in Orion. All right, so feedback. I think the key questions in star formation are these three. What determines the masses of stars, the so-called initial mass function? Why does the so-called star formation efficiency look? That is, by the time you convert a few percent of the mass of the cloud, you blow the cloud apart. Why? It must be feedback. What determines the star formation rate? These are some key questions. And my bottom line is, I think it's a combination of two things. Feedback from star formation itself, but also n-body dynamics. Stars almost always forming clusters and groups where they interact violently. That is the message of Orion. Violent interactions are more common than I think people have thought. So a little bit of feedback physics. I break it down to two aspects. One is the radiation feedback, X-rays, ultraviolet, which heats the gas, of course, ionizes the gas, and then that results in expansion, and of course that drives shocks. And then there's a mechanical feedback. NHD processes drive jets, and that is a universal law. Show me an accreting, spinning, and magnetized system, and I will show you a collimated jet. And there are properties like the Mach number or the flow. The speed is always related to the escape speed from the launch region. It's a universal law, independent of this. It's a young star, a quasar, a black hole, neutron star. Rotation, magnetic fields, and accretion result in outflows. Okay. I talk about what I call the feedback ladder. Really has heard of it. What I mean by this is that as you go down the scale, feedback processes get ever stronger. And if you have a cloud of a certain mass, a certain amount of binding energy, when the feedback can overwhelm and dump more momentum into the cloud than the binding energy of the cloud, you can disrupt the cloud. So if you have a small cloud which has protostars and outflows, the outflows can terminate star formation. That's the end of the story. If, on the other hand, the energy, momentum can be bound up, then you can proceed down the ladder to ever stronger feedback mechanism. The end result of this is when you get to really massive clouds, like the clouds in the galactic center, where you have escape speeds of tens of kilometers per second, masses of millions of solar masses. Examples are the central molecular zone, the nucleus of NAD2, the interacting galaxies like the antennae. We have massive clouds of 100 million solar masses with line widths of 50 kilometers per second. the binding energy is so large that even supernovae will not terminate star formation. In that case, the pressure is what prevents all the mass of the gas from forming onto stars. And I think that's what I call feedback failure is probably the key to forming clusters like larger clusters, which have not formed in the Milky Way for 5 or 6 billion years. So this is what I call the feedback pattern. I'm going to concentrate on this aspect, say a few words about the post-main sequence phases, because I think the star formation process is a complex multi-scale ecology. And Orion is, I think, our best laboratory to study this environment. So this is what I said before, accretion, spin, magnetic fields, maybe radiation in the case of massive stars and black holes, you will have outflow, okay? For the low mass stars, it's almost certainly MHD processes that launch these flows, okay? And the key thing about outflows in young stars is that the momentum is coupled directly into the parent cloud. Whereas if you have supernovae, you follow that a supernova happens well after a post-main sequence lifetime. And the ultraviolet radiation and stellar rings have already blown most of the gas out of the way. So the feedback impact of supernovae on clouds is limited by the fact that the solid angle of the cloud is small. And you're only hitting a portion. Most of the energy of the supernova gets vented to the lowest density medium, often out of the galaxy, if it's a dwarf galaxy, okay? And of course, we know these outflows also can generate turbulence. There's a lot of papers on that. So just a few examples. This is going to be very visual. I'm going to move very quickly because we're wasting 15 minutes. So we're going to go, you prepare, open your brains and just look. This is the classic outflow. One of the rare cases where it's an isolated star in a small 10 solar mass cloud. You see a jet. You do not see the protostar. If I register this to the IRAS view, there's the infrared view. This is registered. The background stars don't move. And now you see a bubble. You see a protostar. And if I then go to ALMA, you see a molecular outflow, redshifted, blue shifted. You see the jet in the Hubble image. And if you don't believe that's a jet, by the way, a message. The outflows seen in molecules are low velocity, few kilometers per second to maybe 10, maybe 100. With optical jets, we're talking about hundreds of kilometers per second and much larger scale. So this is zooming in on the jet, this blue line with Hubble, 3 years apart. This is way back in ancient history, 1994. 3 years later, there it is. See the movement? That's 3 years. And we tried to go back. Hubble wants to be used for cosmology, and star formation guys don't get much time. We keep trying. I wish Hubble was dedicated to taking a picture every 2 years. We'd have the movie by now. Okay. By the way, this jet is that part that you saw. The outflow, when it's back to stars, is much bigger. There's a bow shock here. There's a bow shock here. These are moving at 100 some odd kilometers per second. Molecular outflows tend to be much smaller and restricted to the size of the cloud. When the wind sweeps up molecular gas, you have molecular outflow. When you no longer interact with molecules, you have an atomic or ionized outflow. And the shocks can dissociate the molecules. So the molecules are somewhat of a, so this is taxonomy. How do you ionize part-2? This, of course, is about 1 million times too big. There's a disk, magnetosphere. It drives a wind, which can be recollimated into a jet. The jets are pulsed, variable in every way you can imagine, not just in velocity and mass loss rate, also angle. Ejection directions vary. Sometimes the jets are deflected by side winds. It's as messy as you can possibly imagine. Okay, where you have fast stuff overrunning slow stuff, you get shocks. Where you have, where you have fast stuff outrunning slow stuff, you have nothing. You can't see the material. Because the cooling time and the post-shock gas, typical densities of 10,000 to 1,000 is only a few years. You only see the gas in these images that's currently being shocked. If it's not shocked and there's no radiation field, you don't see it. So I think our mass estimates and therefore momentum and energy estimates are typically lower bounds because we often don't see all the material that's there. Okay, where the stuff finally interacts in a medium, you tend to get a bubble, as you saw in that previous image. And I want to emphasize the point that the molecules trace low velocity, low oxidation gas. The mid-infrared molecules, the high J transitions, trace warmer 1,000-degree gas. And then ions, like carbon plus, will trace the neutral gas or sometimes weakly ionized gas, and then H alpha and recombination lines of hydrogen and even higher excitation ions like oxygen 3 trace your post-shock hot media. And even X-rays in some cases are emitted by these shocks. Okay. I'm going to go over a large range of scales. This is the entire region of Orion. We're looking at about 40 degrees in the sky, the Milky Way. Orion will come back to this. And I'm actually going to go look at that region, the Hyades cluster. Behind the Hyades cluster is one of the first to be studied starting regions called LINS 1551. In that box, I'm going to show you what it looks like with an amateur's telescope. This is from this guy, the MDW survey. This is part of the Hyades stars. This is the LINS 1551 cloud. Tauri is a famous Tauri star, is right there behind the Hyades. The whole cloud structure here points at Orion. Orion has had a huge influence, even in the Taurus clouds. This is the southern part of Taurus. This whole cloud is the influence it knows about Orion. And if you don't believe that, just look at this picture. There's L1551, there's Orion. It points like a vector to this region here, where massive stars have been forming. So I'm going to zoom into LINS 1551. This is a H alpha and sulfur 2 image in these colors. That's the direction to Orion. You see 150 solar mass cloud and about a dozen total stars, including some very famous ones. IRS-5 provides a spectacular perfect parallel shock complex. And it blows out of the cloud. There's a galaxy. There's a shock. Nothing to do with the galaxy. It's a line of sight superposition. I'm going to zoom in to this region. By the way, this is what looks like a single dish. FCRAO map many years ago. Blue shifted CO, low velocity, red shifted CO, tens of kilometers per second. The proper motions and the spectra here show hundreds of kilometers per second in the shocks. Okay. We go back. I'm going to zoom in. This is the IRS-5, it's a binary star, maybe a triple system with 2 jets driving this complex shock system. This loopy structure actually comes from an embedded source here of L50 northeast. You see 2 knots. These are moving at 200 kilometers per second in opposite directions from that invisible source. Okay. And you can see a little close up. I'm going to zoom into the upper region. Here's northeast. This is a famous HH30 jet. We'll zoom into that region and in this region as well. This is HL Tau. Excuse me. So IRS-5. Yeah.
So you say that it is a binary system of protostars?
Yes.
And they are blowing this structure to one side because?
Well, this is a compact jet, very fast. There's a wide angle ring that surrounds it. And it slams into this region. It's illuminating this structure and these shocks in here.
And the contact jet is obscured by a medium.
Yes, it's going on behind the cloud. You see that on the redshift. This thing, no early power, dust obscures it. But here you see it. Okay. And it's unclear whether this jet or these jets power this. It may be a combination of 3 jets. And HH30, you trace it all the way across here. Faintly. Now I'm going to zoom in. There's the HH30. You look at Hubble, edge on this, the inner jet. And then zoom up in here, HL Tauri. There it is. And now with Hubble, this is temporal epochs. You see the main jet comes out this way. There's the ALMA disk, the first to be seen. This is the gas. There's evidence that this guy also has a companion because there's a flow coming down this direction. Look at this shock, the bow shock moving that way. And here's another binary star, XZ Tau. It's blowing this bubble. You can see that bubble expanding. Okay. I just have to show this. This came out a few days ago from James Webb. It's very pretty. I mean, this, you can see this is like a hydrogen. I have nothing else to say about it. This is not my data, but it's just so stunning. I had to show it. Couldn't resist. As I said, almost all stars form in clusters. This is NGC 1333, about 150 young stars. And I'm blinking perfect Hero objects in the optical with near-infrared microhydrogen with Spitzer. You can see it's a confused mess. That's the message. There are a couple of dozen active outflows, and we estimated 2 decades ago that if you just sit on an atom here, the mean time to being hit by a supersonic shock is about 10,000 or 20,000 years. So you're going to reset the chemical clocks. You're going to dissociate the molecules by shocks. And then you're going to recombine and reset the chemical networks, essentially time zero, because there's so many shocks powering disruption of the gas and dissociation of the gas. I just have to superimpose this to observation. This is the same infrared view. See some jets, some various protostars, these shocks, and just to show you what the carbon monoxide red and blue shifted emission looks like, it's a bloody mess. Okay? And this is just a so-called high velocity, meaning 10 kilometers per second gas, which has larger than the escape speed from the cloud, which in this case is 2 kilometers per second escape speed. Okay? This is a small cluster, 150 stars. Okay. And this is just have to show, this is another IRDC that Shuo observed a few years back with ALMA. You know, even in the infrared dark clouds, you see this network of jets. And I think now ALMA has found hundreds of jets in different regions like this one, at the W43 region, others have been studying. Jets are everywhere. And remember, this is just a molecular component. Extinction here is so high, we have no idea what the molecular hydrogen is doing or what the optical emission is doing. James Webb may really help us. And I can't wait to see this cloud, for example, in the James Webb image, where you can penetrate the extinction. All right, I'm going to spend most of the next half hour on Orion, with all the entire winter sky. I'm going to zoom scales from hundreds of parsecs down to the sub-parsec. And there's interactions on between those scales. So this is the Orion region seen in 100 microns. You see the A and B clouds, the Lambda Orionis cloud, the Milky Way, that's the Rosette Nebula. And just to show you, this is registered. So you can see only one star in common. Betelgeuse, very giant. Oops, there it is. There's Betelgeuse. The optical. It has a dusty envelope, so you see it in the infrared. But all the other stars have disappeared, but they're there. And so zooming in a little bit closer, I just want to remind you, Lass's first runaway star. We've known this since Blau in 1951. He discovered that this star, New Columbae, a 09 star, is running away at about 117 kilometers per second. A Auriga, way up there, 150 kilometers per second. They were traced back by Hipparchus to this star, Iota Orionis, 30 minutes below the Orion Nebula. That kind of event just happened in Orion 550 years ago. It's been happening in Orion multiple times. There are many massive runaway stars that have emerged from Orion. All right, so super bubble. This is a nice picture of H alpha. And this is not, whoops. This is showing you the stars and then subtracting the stars. You can see the super bubble. Orion's OB stars have created a 300 parsec bubble, about this big. Barnard's loop, which is thought for decades as the outer edge of the superbubble, is not the outer edge of the superbubble. We think that's just the most recent, e.g. about 300,000-year-old supernova remnant, that basically blown out this way. This is the mystery, because this feature is in the foreground. It's 150 parsecs away, almost the same distance as LINS 1551. I strongly suspect that this indicates that there were some O stars halfway through the Orion Nebula between us and Orion that have exploded the last 5 or 10 million years to create this structure. Rigel may be a member of that group, as is Betelgeuse. Both Betelgeuse and Rigel are foreground, 240, 300 parsecs away from us, as opposed to Orion, which is 400. So I think there's indirect evidence that there was a small group of massive stars between us and Orion that formed maybe 20 million years ago that has now created the bubble and it's merging with the Orion bubble, giving you this complex structure. By the way, the best image of this I've ever seen is this one. This is taken by 3 amateurs. Unfortunately, Dave Middleman passed away. Turns out he's the founder of this project. He was the fund manager for the Harvard Endowment. He's an amateur astronomer and funded Dennis Chico and Sean Walker to do an H-alpha sky survey with amateur hardware. And as far as I can tell, it's the deepest, best H-alpha survey of most of the sky. This is an image they took of the Orion superbubble, which shows all the power shocks and details that I've never seen before. Feedback on a dozen OB stars that formed and died in Orion over the last 20 million years. That's what this picture is telling us. All the active star formation in Orion is happening right here, the Orion Nebula, and right here by NGC 2024 and in Orion B. So that's a huge scale panoramic view, and all this activity is compressing that gas here, shaping Orion's that A cloud.
Excuse me, so all those compact objects coming out from those explosions like 20 million years ago, were they probably like fast enough to escape the region, or they are supposed to be more or less running the
So we think something like 30% of all O stars are runaways. They've been ejected from the startling region. So they explode not where they form, they explode far from where they explode. As a result, Orion probably 60% of the stars exploded near their birth sites. Most of the original group is formed up here. And then star formation migrated this way over the last 10 million years. The current star formations will be here. The oldest subgroups are centered here. The 5 million year subgroup, the belt stars are centered here. Orion Nebula is centered here. That's the youngest subgroup. Okay. So there's been a migration of star formation this way. These stars, probably 30% of those O stars were ejected, like A or right and Newfoundland Bay. When they blow up in various locations, injecting additional energy to the stars that blew up right here. But the point is that the H1 shell this big, not this big. Okay, I'm going to zoom in. So this is Barnard's loop.
But sorry to interrupt again.
Sure.
But there are smaller bubbles around the. No, go back to the.
Okay.
There are smaller bubbles in the periphery, 1, 2, 3, some smaller ones.
Like here, yeah.
No, that on the, yeah.
This is all background, by the way. This is the Milky Way. These are much more distant. This is the Rosette Nebula,
Oh, okay.
2024. This is about 1.7 kpc.
Okay,
or
so
so.
background.
So this is all background. This is nothing to do with Orion. This is also background.
But similar.
Similar structures, for similar dynamics. Yeah. But there's a supernova remnant here. There's a complex shell. But this is what I want to pay attention to right now. I'm going to zoom into here with Clunk. So this is the red is a 30 gigahertz, 1 centimeter radio emission. In green is the dust, the Orion A cloud, the Orion B cloud. And then in carbon monoxide, 13, oops, no, there's the this is registered, that's the constellation visually. Another amateur picture by, I don't know, it's a California amateur whose name I should have put on here. Does spectacular astrophotography. So this is registered, Planck, amateur, Planck, amateur. And then zoom in, this is my ancient map, made in 1987, Bell Labs, 7-meter antenna. You see the kinematics, redshifted, blue shifted. Notice that this looks like a giant comet. And the integral shaped filament is the most compressed part. It's the part facing the oldest subgroup of Orion, where all the momentum injection happens. So I think this whole region is shaped by that feedback from massive stars over the last 10 million years or so. Okay, and this is again the Planck image. And then we go to the more modern view, the Karma Orion Survey, Karma NRO Orion Survey that Shua Khan published in 2018. This is 12 CO, optically thick, 13 CO, optically thinner, not thin, but thinner. Colors are kinematics, redshift in the north, blue shift in the south, it's chaotic. And when we zoom in, this is the optical relationship, just the peak antenna temperature in red. Orion Nebula. Notice there's a big cavity to the south. You don't see that in 13 CO, we sure see that in parts of it in 12 CO. And of course, Orion is creating a cavity. And then this is the, just kind of scrolling through the data cube from blue shifted to red shifted. And so this is the blue shifted, believe it or not, low velocity stuff. But I use 3 channels at once, red, green, blue, to show 4 kilometers, 5 kilometers, 6 kilometers of red. Now I take that filter and scroll it through the data cube. So you see the kinematics. I'm not a fan of the moment maps. I think moment maps are what I call data, not reduction, but data destruction. They hide the information that's contained in the full data cube. You really need more sophisticated, I would say, virtual reality tools to actually to visualize and analyze data cubes. Moment maps are terrible, in my opinion. They hide the physics. So I prefer this kind of display. Here's the whole kinematics of the cloud. So going back and forth from red to blue. Blue shifted here at 4, and then going up. You see a lot of detail. And if we're interested in outflows, this is the high velocity beams. This gets, you can see the Orion explosions. This is a dot. You see a bunch of jets in this one, bunch of little jet-like things, all pretty low velocity compared to the optical. See some big flows down here. What does this look like in the optical? Well, let's see. H alpha. Oops, this is just a map of the outflows. I'll skip that. I'm zooming on this lower complex that you saw here. Okay, see what that is in the optical. There it is. Well, we recognize L1641N, a small cluster. V380 Ori, George Hervey's first Hervey AE star. What does this look like in the optical? There's the optical view. V380 with reflection nebula. HH1 and 2 discovered by George Hervey Guillermo Haro of Mexico, 1949 and 1950. By the way, if you don't know this, go write or book George Hervey's biography. It's available for free on the U of H University of Hawaii website. It's a fantastic read. 3 levels. An astronomy career from growing up as a kid in Los Angeles, becoming one of the best star formation astronomers on the planet. It's a fantastic lesson on astrophysiology. George learned his skills by developing photographic plates at Griffith Observatory, ended his career by observing with the visual spectrograph on the Keck telescope. And it's a great introduction to star formation. I recommend it to all students. It's fabulous. And you learn a lot about history of astronomy, about star formation, and about what it takes to be an astronomer. Really, really cool book. You can pick it up for free on Bo Reicher's website. If you can't find it, email Bo. Anyway, what we discovered lately, V380 drives this Hervey Haro object called not 34, but HH222 up here. There's this bow shock, HH401. We trace it back to the infrared source that powers HH1 and 2. And there's counterflows associated with those shocks. Okay, and notice that there's almost no correspondence between the carbon monoxide. Okay, this is registered. Okay, I'm going to zoom up to the upper corner here. So we saw these 2 shocks. Zoom into the famous HH34 flow. It's a low mass protostar. Arrives at one-sided jet, although this counter jet that's hidden by the cloud. A chain of shocks which tells us that mass loss is episodic, accretion that drives mass loss is episodic, and pulse. And also this gentle S-shaped symmetry. The jet orientations are changing over time. Okay. All right. So let's say a few words about HH24, this interesting region, Orion B. This parsec scale flow can be traced all the way up here. Okay? I'm going to concentrate on these inner jets, because this is a small cluster of about a dozen protostars, maybe 15 protostars, at least half of which are doubles, multiples. Almost all stars are born multiples, and the field star population, think, is produced by dynamical decay of non-hierarchical multiples. When you look at the class zeros binaricity statistics, most class zeros are multiples. You get to class 1, the multiplicity fraction goes down. By the time you get to class 2 and 3, it's almost a field star population. We think in regions like this, almost all stars are born in non-hierarchical multiples, which are violently unstable to dynamical interactions. Okay. So this is a zoom in with the Subaru. You can see now in Sulfur 2 a jet, a counter jet. In green you see H alpha. There's another jet here, third jet here. Here's an HST view of iron 2. This is the view of the collimated jet. It hits a cloud, gets deflected. The jet proper motions are 250 kilometers per second. Molecular outflow is this big. The optical outflow is something like 5 parsecs long. CO outflow is only tiny, 10 to the parsec. These are the protostars that we found with all. This is the paper that Bo's writing with 56 figures. Opus Groundus that requires a week to read. It's going to be published in AJ. This is the parsec scale flow. This is 5 arc minutes. So we're talking about half a degree to chase redshifted low velocity carbon monoxide and shocks along an axis defined by these lines, all emerging from the so-called at strong and Verba 63 region, which is the original infrared nomenclature. So this is the jet. This is the IRS sources. Point out this star. H alpha 5, 4, 1, 2, and 3 are, we think, orphan ground dwarfs or low mass stars. We think all of them were ejected from this little group. Evidence for that from Gaia DR3. This star is moving that way. This is the error cone, tracing back its motion over 6,000 years. The speed is 26 kilometers per second plus or minus 1 from proper motions. There is an example of a dynamical decay of a non-hierarchical multiple star system. You think probably northeast, which is a 2 solar mass protostar in here. EA is a binary, EE is a binary. This one is driving this spectacular jet and it's counterflow in that direction. Read the 56-page paper when it comes out. All right, I'm going to zoom into Orion. This is actually before Orion, I have to mention this is another paper I'm working on. This is actually from Rodriguez, and it's the HH8081's driving source, an IRAS source in Sagittarius, which has, as far as I know, the speed record for a protostellar jet. Radio proper motions indicate 1,200 kilometers per second. There's a radio jet. We're studying the Herbig-Haro object complex associated with this. HH81 and 8081, shown here in the radio. Those are also X-ray sources, hard X-rays with 5 kilovolt X-rays emerging. When you look in the Hubble, this is the Hubble image. This the driving source of 20 solar mass protostars off scale up there. A chain of Herbig-Haro objects which exhibit very high excitation oxygen-free emission. We use multi-epoch Hubble images from 1995, 2018 to measure proper motions. And what we find, shown next, this vector is 1,200 kilometers per second. That's the fastest protostellar outflow I know of. Drive very hard X-ray bright shocks, traced by oxygen-free. And you think this is like almost supernova scale velocities? Well, you're right. By the way, there's a counterflow. The whole outflow is probably about 10 parsecs long in this case. Truly gigantic flow. And we look down below on the axis of the radio jet, about 5 parsecs from the source, you see what looks like a high excitation bubble of hydrogen alpha emission. Now, the jet is apparently hitting obstacles, flow material so fast, it's causing a hot plasma, million-degree plasma to expand adiabatically. And the sideways expansion is shocking against the ambient interstellar medium, just like a supernova. This is a protostellar jet. So protostars can be much more energetic than previously thought. That's the message. All right. Just a reminder of a figure here. There's a message here is that the source luminosity of a protostar correlates with the mechanical power of its outflow. And so this is mechanical force in strange solar mass kilometers per second per year units versus luminosity, proxy for mass. So low mass stars over here, high mass stars over there. The squares are solid squares are class 1, the empty squares are class 0 sources. It's a huge dispersion, or towards a magnitude. But when you look at this large range of mass and luminosity, the mass of protostars may indicate they drive the most powerful outflows. Okay?
But sorry, John, these luminosities, are they all dominated by the accretion luminosities or not?
No, that, well, down here probably accretion luminosity dominated, that's the class 0. Up here, certainly not. Almost certainly it's a thermonuclear. You know, these massive protostars form fast. They ignite hydrogen, go through, you know, the first stages of nuclear burning. So nuclear luminosity dominates up here, even though they're already still accreting.
So for those guys, what is the mechanical force you're measuring?
These are outflows. These are the outflow properties for the mean CO. And I got to caution that this is using molecules. And I will caution that in cases like HH8081 or the GG27 source or Orion, the CO probably underestimates the mechanical power because you're only using one tracer. I always tell students there's no such thing as a perfect tracer. Every tracer has a unique properties, the conditions of traces. So be careful. These are probably lower bounds. In all honesty.
These are not necessarily jets, but just the outflow that the new
Correct.
are.
Yeah. Total momentum or force, momentum injection rate, if you like. Okay, it's not energy conserving because the shocks radiate away your energy. So we really care about the momentum in the flows. And of course, Charlie Law used to say momentum is zero. Yeah, because bipolar, so MV. So I need the absolute magnitude of momentum, right? Forget the sign.
So then this velocity of like 1,100 kilometers per second is related because it's a very high mass star which has a very high condition.
So m dot v is high. So the mass divided by some dynamical time scale.
It's like all that, right?
Yeah, but again, a caution, this is based on carbon monoxide only. We're not accounting for any other tracers like optical emission or shock like hydrogen. So lower bounds. All right, so we'll zoom into Orion quickly. The Orion Nebula again. And this is just against looking at, now I show you the channels, the 5, 7, and 9 times per second. This lines up beautifully with the edge of the nebula. And if I can see that reddish emission, in this image, this is a hand in glove. This filament, this shows up. That is that red feature or green feature here. It's like hand in glove. You see the carbon monoxide that says dust. That lies in front of M43. All right. And what I'm going to do is kind of look through the data cube, and you start seeing the OMC1 cavity, giant cavities on this axis. Notice filamentation in this direction, cavities in this direction. As OMC1 and trapezium stars gain their mass, they must have power, the most powerful outflows in the Orion Nebula region. And so one of the things we did with the carbon Orion data is look for fossil outflow cavities that Orion's massive stars produce as they're performing. And I think we found them. Look through the data cube. Here's some of the high velocity gas. On this axis, there's a redshift lobe way out here. This axis of that cavity traces back to either OMC1 or the trapezium. There's another flow going down this way we identified in 2001 called HH400, which traces back to theta 1 Orion C, we think, although that's not unique. And there's also evidence in this direction as outflows, fossil outflow cavities. Okay, as this massive stars form. And this, in fact, is written up in a series of papers by Umid Kabak, students from Leiden a few years ago. There's OMC1, HH400 is a flow this way. We think this is one of the suspected fossil outflow lobes that can be traced out that way in carbon plus. But I'm going to zoom in to OMC1. Because I think that's what all this is, just comparing the Orion, actually Spitzer image of Orion, showing the bubble in Spitzer and the carbon monoxide in carbon Orion. And I think this is a giant outflow lobe produced by one or more of the massive stars that today light up the nebula, and possibly the precursor to the explosion that happened in OMC1 550 years ago. Okay. Let's skip through this quickly. So I'm going to come back to the Orion Nebula itself, and to get the best images, this facility in Gemini South has a laser guide star set up in which you have 5 lasers, makes a little constellation. It means that we can correct an 80 arc-second field to the diffraction limit of an 8-meter telescope. It's really, really cool. And so here's what we see in Orion. There's a trapezium. You see the network of Orion's fingers. Blue is iron 2. Orange is shocked molecular hydrogen. And to show you some full detail, I scroll it up at full resolution. iron tube fingernails of proper motions of up to 400 kilometers per second in the fingertips. You see these wakes. And then coming to the core region, that's the Beckman-Nogebauer object. Not the full field. And then I'm going to show you the proper motions. So now we're going to compare the Subaru 1999. Good seeing, not adaptive optics corrected. I'm going to blink this to the 2013 Gemini image. This is 14 years later. You see the movement? That is an explosion. Okay, and we think it's associated with runaway star. The Beckman-Nogebauer object has been known to be a runaway at 30 kilometers per second, moving to the northwest. Source I, which you can't see here because it's totally embedded still, we'll come back in a minute. Moving at 10 to the south, and then I want you to pay attention to this guy. And I'll give away the punchline. That's 3 solar mass star is moving away 55 kilometers per second. And if you don't believe it, not too often we can see stars move in the sky with images taken a few years apart. And it traces right back to the core. So we armed with this, we went to ALMA, and here's what ALMA shows. The red shifted gas in red, blue shifted gas in blue. The velocities I'll show in a second are high, up to 100 kilometers per second, but not 400, which is what we see in CO, in iron tube. CO, we see much lower speed. Here's the runaway stars. The vectors correspond to the expected motion over the next 2,000 years. This is source X, 3 solar masses, 55 kilometers per second. The Beckman-Nogebauer about 10 solar masses moving that way. Proper motion of 26. Full speed is about 30. It's redshifted, it's moving into the cloud. Source I, 15 solar masses, given this mass, moving at 13, and it's going to emerge next 40,000 years into the Orion Nebula. We'll have one more UV source, and your great grandchildren may see a new more spectacular nebula in 40,000 years. Here's the kinematics. This shows you in the optical astronomer a long slit spectrum. The bottom of this spectrum is minus 120 kilometers per second. The top is plus 120. In the middle is the over-resolved Orion cloud. This is the molecular cloud itself. These are the streamers that you just saw, the kinematics. Notice the linear velocity gradients. This looks like wakes produced by shrapnel flying out.
So all these fingers, they are formed by dense fragments which came out from the explosion. They are not the stars. I mean, they are pieces of material which is dense and moving very fast.
Yeah, moving very fast in a Hubble flow fashion. You look through the data cube, the moment map destroys the data, you have to look at this as a movie. What you see is you go from low velocity to high velocity, linear velocity gradients. Looks like a hand grenade went off in Orion with an energy of 10 to the 48 Earths. Okay, so we modeled it. Okay. Devin Silva had an ENSO code. So this is the image. This is the cartoon. The model of the ENSO was a blob 1,000 times denser than the ambient medium, moving at Mach 1,000. Okay, and we follow the shocks. This is the result of the model after about 1,000 years. Okay, and I removed that. I don't have time to show it, but you can see these things kind of blobs. They expand a little bit and then they slow down, fragment, and reproduces what we observed here quite beautifully. We don't know what creates these blobs. One suspicion. It's a general characteristic of explosions in dense media. In other words, you have a hand grenade going off in a sphere of glass particles. I have high-speed videos of this from an experiment some group in Canada. What you do with 100 grams of C4 military explosive? Well, you take it out to your backyard, put it inside a set of glass spheres, and take a high-speed movie. And what you get is things that look just like Orion's fingers. Quite remarkable. And anyway, I'm running out of time, so. All right. Just want to show you what the source region looks like, and then we'll stop. So we're going to go back. This is the old VLA map from 2016. showing you a 6 centimeter radio emission. This is Orion Nebula's core trapesium region. This is the OMC1 region. I marked source I, B, N, and X. Can't need see X as the radio source. And along with their proper motions, you can see some of the profiles. And I'm going to just change your view different wavelengths here, all registered. So this is 6 centimeters without the labels. You can see the sources that turn off the labels. Okay. If you now see the point source of source I, the Beckman-Logan object, you do not see X source X. This is a proplet. You see this in a Hubble image. This is radio. This is HST Hubble. Okay. So you don't see OMC1's massive stars because they're too embedded, but you see that proplet. There it is. And then this is near infrared, 1.6 micron. You can see the star, you can see this shadow here. That's the Nova object, source by missing. Okay, this is the cycle 0, cycle 1 continuum, a very low resolution of the dust continuum. Still registered. You can actually see source, the Nova object has a small disk. Okay. You can see source I a little bit too. This is 11.7 micron continuum. This is saturated. That's a Beckman-Logan object. Don't see source I. I heard a rumor that with James Webb, Mark McCarthy has detected source I for the first time in infrared. A rumor. We'll see. He already has the Orion explosion data. I haven't seen it yet, but he says it is awesome. I can't wait. This is our adaptive optics image, all registered. So just going back, multi-wavelength. Here's the Hubble. Here's the VLA. Here's Hubble. Here's 1.6 microns, 1.3 millimeter continuum, low resolution, 11.7 micron continuum with Gemini. And then the molecular hydrogen from the core. And then I'm going to go to ALMA at high resolution, 14 kilometer baseline. Here's source I's disk. Now let's pull this. Okay, this is just registered. Okay, just to remind you what the 6 centimeter looks like, what ALMA looks like. Now I'm going to zoom in. So that's 1 arc second up there. There's the source I disk. DN is now out of the picture. This is the VLA in the same scale, so you don't see the disk in the VLA. There's the disk edge on. And of course, Adam Ginsberg, there's a little outflow, young outflow. This is in the weird molecule SIS, okay? Color-coded velocity. So this is the source I outflow, very young, less than a few hundred years old. There's the accretion disk, rotation curve, and we found 2 unidentified lines. One turns out to be a high-line state of water vapor, about 2,000 K above ground. And the other line we use for this turns out to be sodium fluoride, salt. And when Adam discovered this, he said, wait a minute, we have a whole bunch of other V lines in Orion. About 50 of them turned out to be sodium chloride, potassium chloride, and isotopes of sodium. So all of a sudden we found interstellar salt, no pepper, just salt. And we were able to fit a rotation curve to get the mass, to get these whole masses. All right, that's it. Just want to show you what we think happened here. This is a cartoon that Nick Mogul made about 15 years ago. It's a cartoon. N-body interactions. We use N-body physics correctly, but the hydrodynamics highly incorrectly, which is how the background potential and just assumed by magic. As the gas gets bonded or heated, it just gets replenished by magic. Okay, it didn't follow self-consistent hydrodynamics. But we follow the orbital motion in the presence of the gas, calculating both the Bond-Dihol accretion and the total mass growth of the star in the Bond-Dihol accretion. And so this runs, this is just a cartoon, oops, to illustrate what happens. The most massive seeds happen to plunge to the core, get massive, they interact dynamically and eject each other. I think this is one mechanism for producing runaway stars like AER-LIGA, Nucleon, EN object. And these dynamic interactions are also responsible for explosive outflows. And these explosions can inject a huge amount of momentum directly into the parent cloud in an isotropic fashion. So how common are they? So this is a summary of Orion. We think this guy was ejected from source I. Source I is probably a merger, remnant. two massive stars, or maybe a solar mass star and a 14 solar mass star collided and a 15 solar mass star. And in that process, released 10 to 40 years, the flash of infrared light and X-rays and UV blew apart the cloud core, and that's where the fragments originated. That's where the debris, the dense ejecta came from. We think that's one model. Nick Scoville suggested years ago that maybe there's a protoplanet exists with protoplanets, and you just shot out all the protoplanets. I don't know. We don't know the details of where the ejecta comes from, and this needs to be modeled. I'm looking for Paolo here. We'd love to have numerical simulations of what really happens in a self-consistent way when you combine n-body and hydrodynamics in these violent interactions. I think Orion's not unique. Now we've found about a half dozen other explosion candidates in the Milky Way. This is one of them. G34.15, and I have new ALMA data, which I haven't fully combined yet, so not yet ready to show. We'll see if that has an explosion, but there's another region we found, DR21, which does exhibit evident Hubble Flow schemas that trace back to an explosion about 10,000 years ago. That was far more energetic, almost supernova scale, 10 to the 50 years that happened here. And finally, our most recent result just published this year, Sharpless 106, where we see a Hubble Flow proper motion field in the nebular ejecta with speeds reaching 150 kilometers per second. This is not thermal expansion of an H2 region. This, we think, is an explosion happened 3,500 years ago that's been subsequently ionized by the central O9 star, which is still highly embedded, 0.4 steam right there, S106IR. And I think with that, I'm going to come to my conclusions and stop. We went a few minutes over, but 15 minutes monkeying with the laptop. So, anyway, main messages, I think feedback is multi-scale, happens on scales of AUs to hundreds of parsecs. And it's you can't just zoom in and ignore the large scales. You can't, in the small scales, can't ignore the large scales. The Orion A region, I suspect, is the result of supernova feedback in the superbubble. The cloud has been crushed by the internal pressure of the superbubble. That's why Orion A is on the northern edge of the Orion A cloud. That's why the Orion Nebula is where it is. It's the compression from the superbubble that's triggered it. And in the Orion B cloud, the same story. Ending 2024, the western edge of the Orion B cloud, not for random reasons, but because that's where the maximal compression from the superbubble has happened. Yeah. I think it's not just feedback that limits the efficiency of star formation. I think it's that plus n-body dynamics. Okay. The point being here, if you eject a star into the brown dwarf, it's been removed from its feeding zone. It can't grow anymore unless you bond the oil accrete. Okay. And if you're moving fast, you're not going to feed very much. Okay. If you don't eject a star, and the feedback doesn't strip away the envelope and the source cloud that can feed that envelope, what prevents that star from swallowing all the gas around it? It can go to be a massive star. So I think the stochastic behavior of dynamical interactions in non-hierarchical multiple systems is an absolutely key and vital ingredient in establishing stellar masses and the initial mass function of stars. And let me stop with that.
Okay, question. Yeah, one question about this image of year 21. Is Outposts?
This one is not yet published. This is an Apache Point, like a hydrogen image I took a few years back. We have a really nice narrow band F10 system, so 0.5% filter. So, and I have an offline continuum focus. So really deep H2 imaging. That's the result of that. But yeah, I'm waiting to finish the data on the ALMA, or the new data, the two combinations of the 40-year array plus 70-year array. And then we'll combine it with this image to publish it. But no, it's not published yet. Yes.
Oh, yeah, very interesting talk, a lot of information.
I'll give Paolo the talk.
Oh,
I don't know if he recorded or not. But
Did we record it? Yeah, it's also recorded. It will go on the YouTube channel of the institute, but we will also have a PDF file to distribute.
yeah, that would be great. So maybe I have a question, a comment, like, question is like you mentioned that they were like binary stars, that they were driving very energetic outflows. So what is the effect of binarity in the outflow? Like, are this, like, is it just energetic, is the mass transit in the companion, or like tens of billion?
Yeah. Let me show you something. I had something I pulled out of the talk because it's really too long. This guy, CPSA, another massive star. All will never observe this. Sadly, it's declination plus 60 degrees. So, I would love to see an all data set, but this has been one of the best known massive protostars. In fact, the second closest actively accreting forming massive star near the sun, next to OMC1. 700 parsec distance. It has a complex hydrogen structure. And decades ago, we wrote a paper on this where we interpreted this in terms of a pulse precessing flow. We think this is a multiple star, double star. And we think that every 2,000 years or so, there's a major eccentric orbit. So Nick Mokel and I realized that if you form a binary by capture, the unique signature of that is that the orbital plane is usually not coplanar with the accretion disk plane. Okay, in which case you have forced precession of the disk. And if you have and the second characteristic of such capture form binaries is that the orbits tend to be very eccentric. And so when you have periastron passage, this companion plunges to the disk, you can trigger a major accretion burst. The star flares, the jet flares, and then the torque changes the orientation of the disk slightly. And we think that happens roughly every 2,000 years in this system. And we can basically think it's 1, 2, 3, 4, and the current radio jet is in this axis. So we think soon you'll see another few thousand years, you'll see another segment of hydrogen emission come out. So your great grandchildren might see it. But anyway, this is, I think, an example of a pulse processing jet. In other cases, like an HH111, again, a binary star, the HH1, like, I think all the really spectacular jets appear to be multiple. In fact, Bo has argued that it's the stochastic interactions of these low-order multiples in non-hierarchical configurations that triggers the most spectacular outflow activity. And so in HH111, the main jet has a well-defined axis. There's a side jet at almost 90 degrees with respect to the original jet axis. And we see, two jets coming out. In the HH24 region, the EB source, which is the youngest of the embedded protostars, also appears to have what looks like a cross-shaped VLA signature, which we interpret as likely two jets coming off at almost right angles. And so that to me suggests that these multiples are formed not by disk fragmentation, because they're not coplanar. The disk orientations are misaligned. The LINS 1551 does appear to be more or less aligned twin jets. So there it's consistent with what one expects of disk fragmentation. To form, the disk fragments into two protostars, and then each has a little circumstellar disk, which is surrounded by a circumbinary disk. And in that case, the jets are almost co-aligned. But the interactions, if the orbits are not circular, they're not coplanar, tend to be much more violent, and we think that triggers the major accretion events that we see in the most
accretion, but triggers like this jets periodically.
Yeah, so if you have a disk, Nick has actually modeled something like Cephei in our 2009 paper, Nick Mokel. Sadly, lots of field, wish he would have stayed, but he had kids, very hard to survive if you can't get a permanent job. So it's tragic. He and Kathy Clark were developing, and Andy Burkhardt were working on developing a code to combine hydrodynamics and M-body in a proper way. I'm really sad that the field lost him. But he had a model of Cephei specifically, where he shows he's a non-coplanar, highly eccentric companion that plunges through the disk, and it actually triggers these outflow episodes, quasi-periodically. Yeah.
Yeah, this is a high velocity outflow, like 1,200. I mean, that's what we see in accelerometers. It's like it's transient. That's the kind of like energetic parameters. Like those are the velocities that we see. So I don't know if like simulations can predict radiation driven outflows that speed, or if you have to go to like the scenario of a merger.
Yeah, as I said, I think Orion source I is a merger event. It could be a binary, but to get 10 to the 48 out of a system that's 15 solar masses, if it's a binary, you formed it from dragging two stars to infinity, how close do you have to bring them in to release 10 to the 48 thirds of gravitational potential energy? The answer is something like an AU. Now, we know from stochasticity that source I is a cool for this cycle. If you look back in the literature, that way back in Orion is the very first bipolar outpost discovered by Nick Stolberg and John Kwan in 1976. In fact, Bob Wilson, who took the very first CO spectrum ever taken at Kitt Peak in 1970, the very first spectrum taken with 1 pixel at a time, shows the rings, the high velocity rings in light. Go back and you originally discovered carbon monoxide in active letters. It's a really one sentence abstract. Bob Wilson and Arnold Kendricks have 2 great papers. Amongst many others. The first one is discovered at CMB, which I showed students as very elegant because it's a 1 sentence abstract. That's that we discovered excess radio emission that's 5 gigahertz. The whole in today's APJ with the whole entire paper is fit into 1 page. That earned them a Nobel Prize in Physics. The second great paper is discovered carbon monoxide, which is a whole fantastic story because they took Bell Labs are the only receivers that could detect that line. And so I asked the director of NRAO, can we get some telescope time on the 36-foot Kitt Peak? And the director said, well, no one's using it, so yeah, it takes 6 months. So Bell Labs packed up a trailer full of hardware with price bonds and communications receivers and hauled it out to Kitt Peak and set it up. And the telescope didn't come with a drive system. They had to develop the tracking for the 36-foot. So Bell Labs did that for the 36-foot antenna. And then they published the paper, again, 1 page in APJ letters, but I think 2 sentences in the abstract. We discovered carbon monoxide in the Orion Nebula. And the first spectrum shows the 100 kilometer per second line mix. I asked Bob about this. Well, did you realize that this is kind of exceptional? Said, well, no, we just thought that's the way carbon monoxide is. And then a few years later, that paper came out in 1971 in APJ letters. Dependency is Wilson injector. Heat injector built the speaker. 5 years later, Nick Stolberg and John Kwan did a more serious map of Orion and realized something anomalous going on. And in their paper, they thought that the red giant, the red supergiant, is behind the Orion Nebula. That's not chance. And then it was realized by, I think it was 2010 time frame. It was Leonardo Testi took a spectrum of the reflection of velocity to the east of source I with the VLT and realized that the photosphere spectrum of source I is 4,000 Kelvin. It looks like a red giant. Even though now we know it's a 15 solar mass star. It's not an O star. Why? Because the photosphere is bloated. These rapidly feeding stars develop bloated photosphere, AU scale photosphere. So my argument is that if this thing is 4,000 Kelvin and has a luminosity of almost 100,000 L sub, it has to be AU scale. If you try to make a binary with an AU scale orbit, you're going to have common envelope evolution. And that means the stars are going to merge because they have a highly frictional, a highly viscous environment. A protostellar merger, I think, is easy in bloated massive protostars. And so I think mergers amongst massive stars are probably likely because, first of all, most massive stars are multiple. Secondly, votes in multiples is common. And when they're accreting at higher rates, they become bloated. So I think that really favors a scenario in which stellar mergers are common in massive star formation. I think it's unavoidable. And I think that's the recipe for a wildlife explosion. That's the message I get out of this. So.
Okay, interesting to know the rates. So we can observe them.
Louis Zapata is really taking a stab at this. And so from the candidates, half a dozen candidates we now have, he's estimated the rate is at least that of the supernova rate. That suggests that every massive star undergoes at least one merger event in its formation, if that rate is correct. And in fact, I was part of a program called Spirits with Spitzer, at the end of its life, with Manfred Kasloval as a leader. We monitored 200 nearby galaxies with Spitzer about 5 to 6 epochs over since 2014 until the end of Spitzer. And there's about 200 transients in there, most of which are supernovae. There's a number of transients in the Spitzer catalog which could be Orion-like events in nearby galaxies. Not improving. But I think we argued in a paper that Hans Zinnecker in 05, I think, that a protostellar merger like the thing happened in Orion likely produces a very luminous, like 10 to the 7 some infrared flare. It'll look like a supernova, or maybe like an FU Orionis event on steroids. Literally 10 to the 7 sun, which comes up very quickly and then stays bright for years. A Kelvin Helmholtz time scale for the massive merger remedy. And so, for example, Orion could have been bright for say 10 years, a decade, to get rid of its entropy. So Spitzer, or now it's too late for Spitzer, but James Webb has the potential. Problem is, it's not an ideal survey. What we really need is a fisheye lens that monitors a couple hundred galaxies continuously. And I think this the way to find these things is laser flares. That we now know that the major accretion events, like NGC 6334I, sharpest 65 IRS3, in every case had a luminous infrared or submillimeter flare. The water maser and the methanol maser increase the luminosity by a factor of 100. And so major flares may be an early warning sign of a major accretion event, and maybe it mergers. And, so that's I think, the cheapest way. So you guys, the Geddes antenna, I think it's part of the basic global maser monitoring network for methanol majors. I don't know if it is or not, but it is a group that monitors masers, water and methanol. In fact, just last month I did an alert on one of those, and I followed up a maser flare. That was not so spectacular. It's 2 magnitudes, so not impressive in a K-band. But I think maser flare, monitoring maser flares, and then following up in the infrared would be a way to do it. So, for example, it'd be really fun to have a VLA program to look at the 200 spirits galaxies with the VLA like once a month. See if any of the masers flare. Once you see a really luminous maser flare, then you have a POO program for James Webb. You can look there, see if anything has appeared that wasn't there before. Someone young has to do this, not me. Okay.
Great. Thank you very much again.